Hi, Assalamualaikum warahmatullahi wabarakatuh. So today we are going to continue with our physics lecture. Okay, so the topic for today is atomic physics, the early models of the atom, the spectrum of hydrogen atom, the Bohr's model of the hydrogen atom, atomic radiation. So these are the learning outcomes that you should be able to obtain at the end of the lesson. You may refer to these learning outcomes in your lecture notes that has been given before. Okay, so we begin with the early models of the atom. Okay, the first one is J.J. Thomson's model. This is one of the earliest model of the atom. Okay, we usually call this model a plum pudding model because it does look like pudding, okay, to most of the people. Okay, where the electrons are small negative charges at various locations within the atom, and then the positive charge of the atom is distributed continuously in the spherical volume. Okay, and then the second one is the Rutherford model. The Rutherford model is a planetary model. A positive charge is concentrated in the center of the atom called the nucleus. The electron orbit the nucleus like planets orbit the sun. Okay, it really looks like a solar system. But there are problems with Rutherford's model. Okay, the first one, Rutherford's model failed to explain why atoms emit certain discrete characteristic frequencies of electromagnetic radiation. And then the second one is Rutherford's electrons are undergoing a centrifugal acceleration, and so should a radial electromagnetic wave of the same frequency. The radius should steadily decrease as this radiation is given off, and then the electron should eventually spiral into the nucleus, but it doesn't happen. Okay, the problem with the Rutherford model is it cannot explain certain thing. Okay. Okay, so we continue with the second topic, the spectrum of atomic hydrogen. Okay, the emission spectra. If we look at the light emitted by a low pressure gas when subjected to a large electric field, we find a series of individual lines called a line spectrum. This is the line spectrum of hydrogen, okay, from violet, blue, orange to red. Okay, so if you can see here, this is the high voltage difference applied to a low pressure gas. Okay, the light is emitted to the diffraction grating, and then the line spectrum is emitted to the screen. Okay, so that we can see the line spectrum of certain element. For this case is the hydrogen. Okay, the wavelength of hydrogen spectral lines can be found from the Rydberg equation. This is the Rydberg equation, 1 over lambda, or wavelength equals to the Rydberg constant. This is the value of the Rydberg constant times 1 over m square minus 1 over n square. Okay, n is an integer equals to 1, 2, 3, and so on. M also an integer. M and n are energy levels, and must always be greater than n. Okay, m and n are energy levels, or the orbits of the electron. Okay, the number of orbits of the electron. Okay, common spectral lines series of hydrogen. For m equals to 1, it is a Lyman series. For m equals to 2, it is a Balmer series. For m equals to 3, it is a Paschen series. Okay, we're going to explain this series in the next slide. Okay, this is the Lyman series, this is the Balmer series, this is the Bastian series. Okay, we need to focus on the Balmer series because the Balmer series covers the visible light spectrum from 400 nanometers to 700 nanometers for the visible light range. Okay, for Balmer series, the emission spectrum ends at energy level 2. Okay, examples of spectral lines for n equals to 3, lambda mass equals to 656.3 nanometer. For n equals to 4, and lambda equals to 486.1 nanometer. So if you're referring to this equation, n must always be greater than m. Both are energy levels, both are orbits. Okay, let's say for Balmer series, okay, m must always equals to 2. Okay, m must always equals to 2, n must always greater than 2. It can be 3, 4, 5, 6, 7, and so on. And but it cannot be less than 3. It cannot be 2 or it cannot be 1. Okay, similar to for Lyman series. For Lyman series, n must always be 1 and n must be always greater than 1. It can be 2, 3, and so on. Okay. Okay, going back here. For Lyman series, it is a far ultraviolet range. Okay, it ends at energy level 1. For Balmer series, it ends at energy level 2. For Bastian series, it ends at energy level 3. Okay. Other than emission spectra, we also have absorption spectra. Okay, an element can also absorb light at specific wavelength. Okay, if you can recall in the last slide, a hydrogen atom emits certain lines of spectrum, but here that same element can also absorb light. Okay, can absorb certain spectrum of certain lines of the spectrum. Okay, the absorption spectrum consists of a series of dark lines superimposed on the otherwise continuous spectrum. The continuous spectrum emitted by the sun passes through the cooler gases of the sun's atmosphere. The various absorption lines can be used to identify elements in the solar atmosphere, and then this led to the discovery of helium. That's why we know that on the surface of the sun, helium exists there, because certain lines of spectrum we cannot measure on the Earth. The light emitted by the sun, the spectrum of light emitted by sun missing certain lines, and then what is these missing lines? These missing lines fit the characteristic of helium, where this line has been absorbed by helium. Okay, so that we conclude that on the sun there is helium. Okay, so the next topic, Bohr's model of the hydrogen atom. So in 1913, Niels Bohr provide an explanation of atomic spectra that includes some features of the currently accepted theory. Okay, so these are the Bohr assumption for hydrogen. The electron move in circular orbits around the proton under the influence of the Coulomb force of attraction. Okay, you can see here, this is the proton, this is the electron. The electron will orbit the proton, okay, in a circular orbit. Okay, because electron is has a negative charge, and then proton has a positive charge. Coulomb force will exist between them. Okay, second, only certain electron orbits are stable and allowed. Okay, this is the most important thing. You need to know that not all orbits are allowed, only certain orbits are allowed. By saying orbits, I mean the energy level. Only energy level is only certain energy level are stable, and only certain energy level are allowed for the electron to be in it. Okay, third one, radiation is emitted by the atom when the electron jumps from a more energetic initial state to a less energetic state. The frequency is given by this equation. Okay, this is also a very important equation. When the light is emitted or the light is absorbed, we want to know what is the change of energy between the energy level. Okay, the change of energy or the change of energy level equals to E final or energy final minus energy initial equals to HF. H is the Planck constant, F is the frequency of the light emitted or the light absorbed. Okay, and then the fourth one, the circumference of the allowed electron orbits is determined by a condition imposed on the electron's orbital angular momentum. So the circumference of the electron's orbit must contain an integral number of the Vuille wavelength, where 2 pi r equals to m lambda, and then m. Okay, m equals to 1, 2, 3, and so on. Okay, this is also important because only certain orbit is allowed, and then the circumference must fulfill the condition where it must fit the wavelength of the light emitted or absorbed. Okay, for example, this one, if you can see here, this is the circumference of the orbit. Okay, the circle one, the circumference of the orbit inside. Okay, this is the wavelength starting from here. Okay, this is half wavelength, 1 wavelength, 2 wavelength, and then 3 wavelength. Okay, it fits 3 wavelength in this circumference, so it must fit an integral number of the Bohr wavelength. Okay, so that the orbit will be stable, and the then electron allowed to be in that orbit. If it cannot fit the lambda, the wavelength, the electron cannot be in that orbit. Okay, again, this is 1 lambda, 2 lambda, 3 lambda. Okay. Okay, this is the radius of the atomic orbit. Okay, this is the nucleus, this is the first orbit, second orbit, third orbit. By saying orbit, I mean the energy level, the first energy level, second energy level, third energy level, and so on until infinity. The radii of the Bohr orbits are quantized and given by the following equation. So this is the equation: Rn equals to n square h bar square over me times ke e square, and n equals to 1, 2, 3. Based on Bohr assumption, the electron can only exist in certain allowed orbits determined by the integer n. When n equals to 1, the orbit has the smallest radius called the Bohr radius. A node equals to 0.0529 nanometers. Then general expression for the radius of any orbit in a hydrogen atom is or can be calculated by using this equation: Rn equals to n square a node, okay, or n square times 0.0529 nanometers. So for second energy level, you can replace n with 2. For the third energy level, you can replace n with 3. For the fourth energy level, you can replace n with 4. Okay, and of course for the first energy level or the ground state, you can just replace n equals to 1. So 1 square equals to 1 times a. Okay, it will give you the original a for first for the first energy level or the first radius. Okay, so this is the energy levels for the atomic orbit. Okay, I will explain this energy level in the next video. So here the energy of any orbit can be calculated by using this equation. Okay, the lowest energy level is called the ground state. Okay, correspond to n equals to 1, where the energy is negative 13.6 electron volt. The next energy level has an energy of negative 3.4 electron volt. The uppermost energy level corresponds to n approaching infinity, where the energy equals to 0. So in this video, I'm going to explain about energy level diagram. On your screen is the energy level of the atom in the form of orbit. Okay, orbit 1 and 1, orbit 2 and 2, orbit 3 and 3. So the orbit also represent the energy level 1, energy level 2, and energy level 3. But it is quite difficult to draw this kind of diagram, because you need lots of orbits, and then it's quite difficult to draw the transition between the orbits. That's why you need the energy level diagram. So it makes easier for you to draw and the transition lines, to see the energy levels, to see the difference between the energy level, and is it more convenient for you to understand the transition. Okay, so from the previous energy level, we convert the energy level to the energy level diagram. This is the ground state, the second state or the second orbit, the third orbit or the third energy state, fourth, 5, 6, 7, and so on until infinity. Okay, this is the ground state, or the orbit number 1, or the energy level number 1, the energy level number 2, the energy level number 3. Okay, and then the energy level number 4, the energy level number 5, the energy level number 6, and then the energy level number 7. Okay, until you can draw the level until infinity. And then the energy level associated with this equation for the energy equals to minus 13.6 divided by n square electron volt. So the energy level 1 equals to negative 13.6 divided by n square. N is the orbit of the electron, equals to negative 13.6 electron volt. That's for the ground state, the first orbit. For the second orbit, for the second energy state, E2 equals to negative 13.6 over 2 square equals to 3.401, negative 3.401 electron volt. Okay, the first state, the second state, and then the third energy state equals to E3 negative 13.6 divided by 3 square equals to negative 1.512 electron volt. Okay, and then the third one, E4 equals to 13.6 over 4 square equals to negative 0.8504 electron volt. And the fifth one, energy level E5 equals to negative 13.6, 5 square equals to negative 0.5442 electron volt. Okay, if you can see here, as the energy level increase, okay, the energy will also increase from negative 13.6 electron volt to 0 electron volt. Okay, from the orbit number 1 to orbit infinity. Okay, at the energy level infinity, the energy is 0. So it increased from negative 13.6 electron volt to 0 volt to 0 electron volt. So let's say this is one example, the transition of the energy of the atom. Okay, the transition from energy level 3 to energy level 2. Okay, the energy drop from energy level 3 to energy level number 2. For this is for Balmer series. Okay, the change of energy equals to final energy minus initial energy equals to negative 3.401 minus 1.512. Okay, and the result is, okay, wait for me to calculate the value first. Okay, so at the meantime, when the energy drop from energy level 3 to energy level 2, certain energy will be released. Okay, the energy or the light will be released from the atom. Okay, so we are going to calculate the energy release from the atom. Because of the transition, the energy drop from energy level 3 to energy level number 2. Okay, the value is negative 1.889 electron volt. The most important thing here is the sign negative, the negative sign. The negative sign means that the energy release. Okay, the positive sign, if the positive sign means that energy absorbed. Okay, if you want to imagine what is energy release, you just imagine that the light is emitted from the atom. Okay, when the light is emitted from the atom, then we can say the energy is released. Okay, the transition is from the higher energy level to a lower energy level. Let's say if we have energy level from a lower energy level to a higher energy level, the light will be absorbed. We can say that the light is absorbed. Okay, let's say if the transition between N2 to N3, energy level 2 to energy level 3, the energy will be gained, and then the energy difference equals to positive 1.889, okay, electron volt. Similar from E3 to E2, the magnitude of energy is the same, the difference of energy is the same. The only difference is the sign. Negative shows that energy is emitted, positive shows that energy is absorbed. Okay, for example, this one, from energy level 5 to energy level 2. So always you need to find the change of energy final minus energy initial. Okay, so the final energy equals to negative 3.401 electron volt minus energy level 5 negative 0.5442 electron volt. Then the change of energy is, let me calculate first. So here I expect that the sign is negative because the energy drop from energy level 5 to energy level 2. Okay, so here we go. The value for energy, the change of energy is negative 2.8568 electron volt, meaning that the light is emitted from the atom. Okay, another example, from energy level 3 gain to energy level number 5. So I expect the value will be positive because of course the light will be absorbed. So energy level 5, energy level equals to negative 0.5442 minus 1.512. Okay, let me calculate first. Okay, so I expect positive value because the light is absorbed here. Okay, positive 0.9678 electron volts. So that's the value if the light, the transition of light from E3 to E2, E3 to E5, sorry. Okay, if negative, energy is released. If positive, energy is absorbed. Okay, I hope you understand. Then we proceed to the next slide. Okay, the last slide for this session. The characteristic of X-ray production. Okay, for atomic radiation, when a metal target is bombarded by high energy electrons, X-rays are emitted. Okay, so if you can see here, this is the cathode that produces electron beam. Okay, the electron beam will hit the tungsten or anode, and then X-ray beam will be produced in a vacuum chamber. So, but before that, you need to apply direct current high voltage, okay, between cathode and anode, so that the electron beam will be produced and it will hit the tungsten anode. Okay, the X-ray spectrum typically consists of a broad continuous spectrum and a series of sharp lines. The lines are dependent on the metal of the target. The lines are called the characteristic X-rays. Okay, if you can see here the graph of intensity versus the wavelength. Okay, the peak represent characteristic X-ray. Their appearance depends on the target material. Okay, the continuous curve represents Bremsstrahlung. The shortest wavelength depends on the lighting voltage. Okay, if you can see here, this is the incoming projectile electron. Okay, it will hit the electron, and then inside the material, inside the tungsten for this case, and then X-ray will be produced. Okay, the characteristic X-ray emission. Okay, I hope you understand. So we end our session here. If you have any question, then you can just ask me in the Google Classroom. Okay, thank you.